start by talking. Yeah, there's a test on Tuesday. Thank you. So exam 1 is Tuesday the 18th. Yes?
We have a full hour and a half work on it.
Yes. Yes, you will have the full time. Seriously, could you please let me talk now? The topics on this exam are, so the topics are determined by what practice problems this stuff is going to be, the questions on the test are going to be similar to. The first one is all of those units questions, and that includes questions on unit conversions, scientific notation. I think there might be some prefixes problems, but it'll be the kind of questions that are on those problems. And second, there will be some questions on 1D kinematics of particles, but it's only going to be questions like the first 4 practice problems. So 1D kinematics of particles. One through 4. So those are the kind of questions where it says there's, you know, a swimmer on the beach, and the swimmer goes to the raft and then back to the boat and back to the, and you move around the 0 position, the positive direction, and change the graph, and, you know, see how the graph changes. So those are the only 1D particle problems that are going to be on there. Yep. That's right, not any of the new equations, right? Yeah, any equations you need will be given, any conversions you need will be given, so you just need to know how to do it. That's true all semester. I'll give you every formula equation you need, every conversion you need, and you just need to know how to use it. I don't remember, yes, I don't remember if there are any prefix questions on the units problems or not. I'll look and see. That's the one that's yeah, kilometer and stuff. Yes, I will give mega equals times 10 to the 6 if there are those kind of problems. But if there's nothing like that on the units problems, I just forget. Then there won't be anything like that on the test. It might be we only do that in labs. And yeah, you'll have the full class period to work on it. I always try to write these tests to make them an hour long for half the class will be gone in an hour. That's how I try to think of it. So I think you'll have plenty of time. And no notes, but like, you know, I said, I'll give you the equations you need, and you can use any kind of calculator you want. Any other questions about the test? Yes. That sort of depends on what kind of questions I put on there. You know, I can put a lot of questions on if they're unit conversion problems, and not very many if they're those position versus time graph problems. But I'd say on average, a test has 4 problems on it. This one will maybe have as many as 6 because the unit conversion problems are faster. Yes. Yeah, there is. And so the quiz, so the exam, to get ready for the exam, you need to make sure you understand how to do all the problems. To get ready for the quiz, you need to read and reread your class notes. Okay, that's going to be just like things that I've emphasized in class, things I've said in class. Yeah, and everything is going to be cumulative the whole semester, so you need to keep going back and refreshing your memory on the old stuff. Yeah. Any other questions? No, just the practice questions is the practice exam. You know, the questions on the exam will be noticeably similar. You know, like a question you see on the exam, you could go back to the problems and say like, okay, that uses the approach I used in this one. You know. 5 to 10. Yeah, it's just short answer, 1 or 2 word answers usually. Sometimes I'll ask you to define something, and it definitely is weighted towards the stuff that I try to emphasize. You know, the stuff that seems important, the stuff I put a star and say notice. You know, that kind of stuff is almost always on there. Yep. Any other questions? Yes. Anything else? All right. Um, so last time, and so with these being the topics, nothing I'm talking about today is to be on the test on Tuesday. This is all future stuff. Everybody gets up and leaves. No, don't do that. So last time I introduced those constant acceleration equations. Yeah, that is. Yeah. So it's like 11 units problems and 4 kinematics problems. So yeah, the good news is for the first exam, you can be pretty clear what kind of questions is going to be on there. Yeah. Yeah, you can get off on a good foot. You can really focus on that stuff. So last time I introduced the constant acceleration equations. And we did a few problems with like balls rolling and a car stopping. But we haven't yet gotten to the main reason that it makes sense to focus on constant acceleration is what I was planning to write there. We didn't get to the big topic, which is free fall and projectile motion. Okay. So the most important reason that we do kinematics of, well, let's say for studying constant acceleration equations, is that they apply to free fall and projectile motion problems. And those are an important thing in physics. I'm going to use those as synonyms. So, you know, you might think of free fall as just dropping straight down and projectile motion as something being launched out. But I'm going to just call it all free fall. So even if you launch something out of a cannon, once it's released, once it's gone from the cannon, I'm going to say it's in free fall. The definition of one of these problems, so free fall or projectile motion means that no, and I'll say significant, forces act on the object besides gravity. So gravity is acting, but nothing else. And that's true if you shoot a cannonball out of a cannon. There is some air resistance. It has to fight its way through the air, but a cannonball is heavy enough and dense enough that it isn't affected too much by air resistance. And so the only significant force acting on it as it flies through the air is gravity. At one point there was a significant force acting, and that was how the cannon shot it. But once it's alone in the air, it's just feeling gravity. And so this brings up the first common misconception of this class, and I want to really focus on these. So common misconception number one. And when I bring these up, these are the things that people tend to, so most of your experience with balls and skateboards and all the things that you pick up and throw and drop and whatever over your life to this point has given you really good intuition about Physics 1 principles. But there are some things where it tends to be the case that the things that you've grown to believe are true are actually not true. And this is the first one of those. And these kind of things will be on quizzes for sure. Okay, every one of these will be on a quiz sometime. But people often think this. So it's often believed that on a light object and a heavy object both in free fall gravity makes the heavy object fall faster. And you have a lot of experiences that make this seem like a reasonable thing to believe. If you take a bowling ball and a feather, bowling ball and a feather, and you drop them at the same time, the bowling ball is always going to hit the ground first. Okay? And that makes you think that gravity makes these things fall differently. But the key thing to understand is that it's not gravity that does that. The truth is that gravity makes all objects fall the same way regardless of their weight. The only reason you see some objects hit the ground before other objects or let's say the only reason some objects fall faster than others is that they are affected differently by air resistance. Okay, so it isn't gravity that makes a bowling ball fall faster than a feather. It's just that if you drop a feather, its fall is affected more by air resistance than the bowling ball is. And I'll talk about what are the factors that go into air resistance. But what that's saying is if you removed all the air from a tube or whatever, and you remove all the air, suck it all out with a powerful pump, and you drop a bowling ball and a feather at the same time, they'll fall exactly together, hit the ground at the exact same time, because gravity makes everything fall exactly the same. It's the other stuff that affects them differently. Okay, that's a weird thing for people to wrap their heads around most of the time, the first time they're told that. And the smartest people in the world for a long time had this same misconception. But I'm going to show you this awesome video where, yes, in space, well, so where we go in space, everywhere we go in space, maybe not everywhere, but most of the time, like when people are in space, like in orbit around a planet on a space station or something, they still feel gravity. They float because they and the space station are both in free fall around the Earth. That's sort of they float the same way, like if you were on I was going to say, if you were in an elevator that the cable broke, let's not say you, someone else, someone you don't like is in an elevator and the cable breaks and there was a camera inside the elevator, it would look like you were floating in there as you both fell together. And that's what astronauts are doing when they're not really in zero gravity. They just look like they're in zero gravity because they're falling. That's when someone's in orbit. But I guess once you get far enough out away from the Earth that you don't feel its gravity, then there's really no gravity. There's also no air resistance. There is in the spaceship, but outside in space, there's no air resistance. But I'm going to show you a video where they have this incredible facility, this huge facility. It must be super expensive to do this, but they use it for testing aircrafts, and I don't know what they do, what tests they're doing, but and this TV show goes in and they suck all the air out of this gigantic building, so it's truly a vacuum. And then mechanically, they use mechanical arms to drop a bowling ball and a feather, and you see exactly this happen. Because there's no air resistance on either of them, we're going to see the bowling ball and the feather fall together, see the feather smash against the ground and bounce up into the air. It's really crazy looking. They use the mechanical arms because if you suck all the air out of a room, it's very hard to breathe. And it would also make your head explode. And So those are the two main reasons that, so when you see the guy walking around in there talking, they have not sucked the air out yet. You know, we don't just have to, so this is one of the cases where we don't just have to put the information in your heads. We first have to remove some very strongly ingrained thoughts that are actually wrong, you know. So that's something we're going to keep focusing on. If air resistance is negligible, and the next thing we're going to do is talk a little bit about when you can expect air resistance to be more important and less important. But if air resistance is negligible, every object in free fall, and that includes things that are shot, you know, projectile motion too, accelerate downward at about 9.81 meters per second squared. And this acceleration is what's referred to as g. So g is 9.81 meters per second squared. And so when they say, like when in Top Gun, they're like, Goose, we're pulling 7 Gs, or whatever. That's 7 times, they're accelerating at 7 times that. That is, yes, that is on the surface of the Earth, roughly at sea level. Although, so the real number at sea level is 9.8065, and on and on. I think at the top of Mount Everest, you know, that's as far as you can get from sea level, and based on the height, based on the altitude, it's like 9.803 or 4 or something. So it's basically the same. There are little fluctuations, bigger fluctuations than that apparently, depending on the geological structures nearby. So that's a really a bigger influence, is just the local mass, you know, density of the ground, but it doesn't change very much if you're on Earth. On the moon, though, it's 1/6 of that, I think. You know, so yeah, that's just referring to the surface of the Earth. Yep. Okay. So this is what we're going to use when we talk about objects in free fall. We're going to talk about accelerations downward at 9.81 meters per second squared. The thing is, in any real application, there is air. You know, none of the things we're trying to calculate are really like inside a vacuum chamber like that. So how do you know when it's reasonable to ignore the effects of air resistance and when that would give you terrible results. You know, when air resistance is really important to the object's motion. Well, here's an example. So when we talk about something in free fall, we're talking about something, if the only force is gravity, that means that the thing can't be touching anything, okay? And it means that the air resistance is negligible. So is it reasonable to say that any object that is not touching any other objects accelerates downward at around 9.81 meters per second squared? No, that's not true. Think about a helicopter, you know, or an airplane. The only reason that those aren't accelerating downward at 9.81 meters per second squared is air resistance. But air resistance lets them climb up into the air if they want, you know. Same with parachutes and gliders and all this stuff. So there are definitely times where assuming that an object that's not touching anything else accelerates downwards at 9.81 is totally like beyond worthless as an approximation, you know. So we have to talk about what are the cases where we can ignore air resistance. So here are the things that determine air's effect on the object's motion. The first thing is the mass of the object. If you keep all the other things the same, so if all else is equal, an object with a larger mass is less affected by air resistance. So for an example of this, think of dropping a pinball and a ping pong ball off the roof of a building. They both have the same shape, roughly the same size. The only real major difference between them is a pinball is made out of steel or whatever kind of metal, and a ping pong ball is hollow plastic. But if you drop them off a building, the pinball would hit the ground a lot faster than the ping pong ball would, just because the mass is a lot higher. Okay. So the pinball has greater mass. And would hit the ground first. If you drop them inside that vacuum chamber, they would hit at the same time. Actually, you know what would happen if you drop the ping pong ball inside that vacuum chamber? It would explode. It would explode because ping pong balls are manufactured at atmospheric pressure. And so there's like a struggle between the pressure of the atmosphere pushing out and the pressure of the atmosphere pushing in, and it's a tie if you're at atmospheric pressure. If you take all that outer pressure away, that would be cool, actually. Yeah. I wonder. Making a good vacuum is hard. Like, we don't have any equipment that can do that. I'd love to do that, but I don't have a way to. I mean, I don't have a way to do it in a small, like that would be the way to do it, was make a little clear box, but I mean, I don't have the equipment to do it. I mean, well, I don't know. So the way that works is it sucks in air by making a vacuum on the inside, and that sucks the air towards the vacuum because things at high pressure want to go to low pressure. So it makes a low pressure in the air, the vacuum, and the air sucks towards it. But I don't know how, when you say it makes a vacuum, I don't know like what fraction of atmospheric pressure it is. But yes, so they are related. It is. No, that is the idea. Yeah.
I had a teacher who had a custom setup where it was a rubber disc on the bottom with a tube connected to an air electronic. So on top of that, he put a glass little jar thing, but it was all designed to do the same way.
Yeah.
But basically, the air would get pumped out.
Yeah.
It would suck the glass down onto the rubber and make an air seal. And we exploded Twinkies.
That's funny. Yeah, I'd love to do that. I'll start thinking and planning. Okay. Yes. Well, so it makes air resistance affect it less. But yes, so here's what's happening. They have the same shape, and so the force of air resistance is actually the same on the pinball and the ping pong ball. It's the same force of air resistance on both of them. The thing is, though, that to make the ping pong ball fall, remember I said gravity applies different forces based on the mass? So the force of gravity is actually bigger on the ping pong ball than on the pinball than on the ping pong ball. And so the force of gravity wins out over that constant air resistance in the pinball, whereas with the ping pong ball, they're both small, and so the air resistance has an effect, But that kind of stuff will make more sense when we start talking about what forces are and stuff. Okay, so that's the first thing, mass. The second thing is surface area. And it's not exactly surface area, but that's an okay way to think about it loosely. So if you have two things that have the same mass, the thing that has a larger surface area its motion is going to be affected more. Think about what you do when you put on a parachute. You're trying to make a huge surface area so the air has a lot of space to catch hold of you. So if all else is equal, an object with a larger surface area is more affected by the air. So I think the easiest way to think of that is imagine imagine dropping a toy soldier with a parachute along with, you know, a ball of the same mass. The ball will hit the ground first. Because of the large surface area of the parachute. And then the last thing, and this is the thing that matters the most, and when I say the most, I'll show you the equation that puts all these pieces together, and you can sort of see why in lab. But the third thing is the speed. The faster something's going, the more its motion is affected by air resistance. So the faster something goes, the more its motion is affected by air resistance. And this, you know, like I just said, this is the one that has the biggest effect. And the thing that I think of with this, I don't know, I should link some videos of this so you can see what I'm talking about. Yeah? Sorry, say it again. Yeah. Yeah, no, there's no such thing as terminal velocity in a vacuum. Because terminal velocity means that the force of gravity pulling something down is exactly equal to the force of air resistance pushing up. And so in air, everything eventually gets to a terminal velocity because as the thing gets faster and faster, the air resistance force keeps increasing. The gravity force stays constant. And so in air, eventually, no matter what you're talking about, it has a terminal velocity. In a vacuum, there's no air resistance force, so the idea doesn't even, it's not possible, you know? Yeah. Speed of light. I have never heard of air resistance, thought of air resistance for the speed of light, but. Oh, I see what you mean. I see what you mean. Yeah, that's a good point. Yes, you couldn't go faster than the speed of light. What? Yeah.
But I was thinking, like, I know that it gets harder to go towards the speed of light because it takes more energy the faster you go. Mm-hmm. But this is because it's impacting the air resistance more and more. Air in space is going to be particles, whatever. But assuming you were in a vacuum, like a complete vacuum,
yeah,
nothing in there, it would be possible to reach this.
No, because it's not air that does that. it's weird theory of relativity
Oh,
effects. So even in space, that's true.
oh,
That yeah, it's related to EMC squared somehow, but that's about the limit of my knowledge on it. But it doesn't have to do with air. It's true in space too. Okay, so think of this. Okay, you're gonna have to take my word for this if you don't like bicycle racing, but I do, so I'm gonna describe. Okay, so in like the Tour de France, they race 2,000 miles over 3 weeks, 100-mile whatever plus a day for 3 weeks, and through all these races, there aren't very many times where the people who are going to win have a chance to break away from the other people. There's only a handful of races where they can, and the reason for that is that if you try to jump out in front, you have all the air resistance on you, and the people behind you just tuck in and ride behind your wheel, and they have to do so much less work that even the worst pro cyclist could easily ride behind the best pro cyclist, But two of the places where you have the best chance to make up time are in the time trials. And in the time trials, you can't tuck behind someone. You just take off one by one, and they time you how fast you can ride 25 miles or whatever. Okay? So you got that. A time trial is just like you going out by yourself and riding as fast as you can, and then they compare your times at the end. And there are 2 times that you can do time trials. Most of the time trials are on flat roads. And so flat time trials versus the other kinds are time trials where you have to race up a mountain in the Alps. And here's what their suits look like for these time trials. On the ones that are on the flat, let's see. So they look sort of like, okay, they're wearing like, ooh, this is going to be good, I can tell already. He has a tail. Okay, so now how does this all work? So there's a wheel here, a wheel here. Do it. Okay, so something like that. And the thing is, okay, they're wearing like sort of rubberized spandex suits. They're wearing these helmets that look like the cross sections of airplane wings. They're bent all the way over so that the area that's facing the wind is as small as possible. And they go through such minute precautions that even, the cables that connect your brakes and your shifters to in the front to the brakes and the derailleurs in the back, they have those going through the tubes of the bike so that these riders won't have to deal with the extra air resistance of a cable touching the wind, So that's how much air resistance is the only thing they care about. Like, how much does it, like, if you look at these guys, how much does it look like their comfort or like how their suits are all the way zipped up? Obviously, they could put a lot more force into the pedals if they were allowed to wear cooler stuff and, wear a more comfortable helmet and stuff. But that stuff is, so here, air resistance is almost the only thing they care about in these races. You're not allowed to do that. That's why. Otherwise, they would. Yes. Yes. Actually, apparently, they would ride those sort of funny-looking recumbent bikes are apparently way more aerodynamic than, but they're rules, and so they're just doing as much of this stuff as they can within the rules. Yep. Oh yeah, I have seen that. Everyone else is pedaling as hard as they can, and it is. That's crazy. Okay, well, here's what a mountain time trial outfit looks like. So, when you see these guys riding mountain time trials, they're wearing just their regular bike helmets. They're wearing just regular short sleeve shirts and shorts. They don't even bother to have their hands in the lower parts of their. Okay, they don't even bother to put their hands in the lower parts of their handlebars to get more aerodynamic. They look like they're basically like they look like 50 guys you see anytime you get onto the Greenway in Minneapolis, you know? So in these, air resistance isn't a concern. Everything that they're doing is just based on how much force they can apply to the pedals, how cool they can stay, that kind of stuff. And so why is that? I mean, the idea is the same. The reason is that if they're riding on the flat, they can go about 40 miles per hour. And if they're riding up a mountain, they can go about 15 miles an hour. And the difference between 40 miles an hour and 15 miles an hour is enough of a difference to make this the best way to ride fast if you're going 15 miles an hour, and to try to turn yourself into like a bullet or whatever to try to ride fast on the flat. Sort of cool. They're always different. Sometimes there's a little down too, but the thing that seems to affect it the most is the up. Although apparently there are people who are really good at going fast downhill and taking the turns fast and not. Like sometimes you'll be watching the Tour de France and the guy will be like cruising around a turn and you'll all of a sudden see his tires shake and then he'll go right over the cliff. No one's ever died that way, but every time it happens, it's totally scary. Let's stop. Yeah. Okay, that's enough for today, I think. I think you've already learned too much, if anything. Yeah.